Now we will see a version of Campbell theorem for marked point processes. For a marked point process with intensity capital lambda A, let f be a function from Rd cross M to R plus. So here M is the mark space, which can be RL if it's a L vector random variable. For a general workspace, I have denoted it as M. This function is takes two input. One is first the location and second is the mark itself. And it mapped to a real positive number. Then if you recall Campbell theorem, there we said that expected value of summation of function fxi over all point is given as integration over function x fx into capital lambda dx. Here we have, because it's a mark point process, each point has a coordinate and its mark. The function would be function will it's a function. We have to take the function width of the point and the mark both. So here we are interested in computing expected value of summation of fxi comma mi, and this summation is taken over all points in the point process. So just go to each point, find xi and its mark mi, compute the function, do it for every point and add it. And the question is asked, what is the expected value of it? So to compute that, we will again do the same trick. We will first condition on total number of points, okay, which is n, and condition on that the summation inside will become will have deterministic number of terms. So the summation itself can be outside the expectation. So it is en, and then given n, the summation is outside, and then the rest term we have expectation respect to phi, that I can write as expectation respect to xi, and then below term is expectation respect to mi given xi. Okay, so this has two randomness, xi and mi. So once I condition on xi, the rest is expectation mi given xi. So I applied conditional probability law 3 times here. Now if you look at this expression, where you have to take there is a function x comma m is the mark of x, and then you compute the expectation m given x. So if you look at this, this is a conditional expectation, okay? And once you compute the expectation with respect to m, it will be a function of x actually. So yeah, so x will actually remain. If you change x, the expectation will change, okay? This is a function of x, let's call it f prime x. It can also be written as x, because the expectation with respect to mark, so that can also be written as expectation over the mark space of fxm into probability that the mark is in D. Okay, so this is assuming the mark is continuous probability. If mark is take discrete probability, you can just take summation over all range of marks fx comma m into probability that mark takes value m. Okay, so don't get confused. It's just expectation formula. It is a probability multiplied by density and integrated. So if I look at that, I can replace this by f prime x, and this will become just summation of exi of f prime x. Okay. Now this the mark I have computed this expectation inside, so the remaining term is just a function of xi. So this, if I can combine this and n to get expectation with respect to phi. So what I get is expectation with respect to phi of summation of f prime xi. So this is here I can again now apply Campbell theorem, because this is just summation of function of xi. So once I apply Campbell theorem, this will be f prime x lambda dx. Okay. So now I will put back the f prime value. It is the expectation of fxm m given x, and then rest is lambda dx. Okay. Now I will also, so this is a valid answer if I know the expectation of this with respect to mark given x, and I can just integrate with respect to lambda dx. Okay. This also means that you compute how many points are there in the set interval dx, and then for that you compute that what is the expected value of the function over the mark distribution, and then you multiply them and add to get the summation value. There's some different forms. You can also write this one. If you remember, this is uh, nothing but some integration of fxm over the probability space of M. So it is fxm into nu x dm integration over the mark space. Okay. Now, if you recall this, nu x and lambda dx is, if you multiply, they will become the Campbell-Mathis measure, which is C dx cross dm. So this will be just integration of fxm on this Campbell-Mathis measure. So you can see that now this looks like exactly Campbell theorem. The mark point process is a point process with this intensity measure. Okay, so if ximi you take that as a coordinate of the point, the equivalent point process, and then this is just summation over all coordinates, and you get this Campbell-Mathis measure. You multiply by the function, and then you integrate it. So in the past, we have talked about dependent marking. It's a marking where each path is dependent on its neighborhood. Now we can extend it to another more to a completely dependent marking, which is special type of marking where each point is dependent completely on the complete neighborhood, right? Not just one point, but the complete neighborhood. So in that case, you can think that for any point xi, the mark is a function of the point and the complete point process. Okay. So here you take the complete mark point process, and this it will depend on that. Okay. And this is a dependent mark because every point is dependent on the same realization. Okay. So there is some correlation on that. So one example that we have seen in the past is this function can be just number of points in the ball of x comma r, denoting the total number of points in the ball around the point x with radius r. That's a dependent marking. So that was just a function of this. In this example, marking which is dependent only on a point in a small neighborhood of radius r on the points in small neighborhood of radius r. But this can be a function of complete point process. Okay, we can just assign the phi itself as the mark. Okay, so complete phi realization is assigned as a mark to each point. Is the more general marking and include the complete point process. So any property you want to derive now, you can write in terms of the mark. Okay. So this we call as universal marking because this is the most general form of marking, independent marking here. And there's another variant which people use is instead of assigning the raw phi to as a mark, they assign as a local view of the phi as a mark. Okay, local view means that from the point, how does the phi look like? So this just means that you shift the origin to the point, and then you look at the shifted point process. It will look like as you are the center and the point process is around you. Okay, so inherently phi is still same, but I get a different shifted version for each point as a mark. Okay, I can, since if I know x1 and x2 and I know the phi as looked from x1, I can definitely compute how phi will look like from x2. Right, so inherently they are not different. It's just that I'm going to assign a different version of the same object. So recall the point process can be seen from point xi is we shift phi to minus xi. Okay, so the xi is the new origin. So you take points in phi and you shift phi minus xi to get new points. Okay, so if this means the xi itself will become at the origin. This is a shifted version of point process, and it is a neighborhood as viewed from the point. So this is also a stationary marking, right? Because if phi is stationary, and then it doesn't depend where you put the origin, because eventually for this mark you have to shift the origin to the point itself. Okay, uh, and it will result in a stationary mark point process if the original point process is also stationary. So the palm probability of universal marks can be same way defined. The marks here is taken as the complete phi. Mark space is suppose n here. And the Baum distribution of the is and A itself is the complete space of the point process. Okay, recall the mark is phi, and we take this mark space as all the possible values marks can take, and phi can take all values, all possible realizations. So the set of that relation is n. And the mark distribution of the mark will be given as probability that mi belongs to k given that xi belongs to phi. And here mark is phi, so this is just probability that phi belongs to k, condition that xi belongs to phi. Okay, and this is nothing but the conditional distribution of phi. Given that there is a point at xi, what will be the look of phi? What is the probability that phi takes a particular value, particular properties k? Okay, so probability of k in also would we say it is a conditional distribution, and we denote it again px phi belongs to k, which means condition on x belonging to phi. What is the probability that phi has this property k? Okay, so explicitly you can also say probability that the phi has property k given that x belongs to phi. Okay, and this property can be how many points are there in a radius r around a point of p2. Okay, so condition on there is a point. What is the probability? How many points are there in a radius r? Okay, so this can you can deduce from this, because if you know, you can compute the condition on the phi. What phi would be says that they will have these many points. So from that you can compute k. So instead of a general x, we can just also take origin O. So this will be probability of 0, condition that origin belongs to the point process. There is a point at the origin in the point process. What is the probability that phi has a property k? Okay, so this is the probability of k, and if it's a stationary point process, it will not depend on x. So you can take x anywhere, so you can just take on the origin. And what is a similar concept is the reduced palm probability. In this, it's also a conditional probability. It's just that when you're looking at the property, whether phi has a property k or not, you don't include the point you are conditioning on. Okay, so you have to remove that typical point on you which you are conditioning, and then ask how the neighborhood looks. Okay, so the notation here is x factorial, and this just means that you are conditioning on x, but you are not including x in the calculation of this. So I want to ask whether phi belongs to k, phi has this property k or not, but I inherently remove x from that. So this is just that probability that condition on x belongs to phi, probability that phi minus this point. Okay, so you remove this point, that point process that it has a property k or not. Okay, so phi minus set minus x is the point process after removal of the point at x. And if x is equal to its origin, then the same thing you can define. This is the 0 factorial, means that you're conditioning that there is a point at the origin, but you are not including that point in the above calculations. Okay, so suppose I have, let's take an example. Suppose K is this property that is made from all realizations, as that realization has one point at the origin. Okay, so this is the property I want to know. So what is the probability? This one, phi belongs to K. This is the probability. What is the probability that phi has property K means? What is the probability that phi has one point at the origin? So suppose we take the Poisson point process with the uniform density. Then probability that there is a point at the origin, that is 0. Okay, so probability that the point is anywhere, it is 0. Now I say this one. What is the probability that give condition that there is a point at the origin? What is the probability that the point process has one point? Okay, and that is going to be 1, because we are conditioning that there is a 1 point at the origin. So phi will definitely have 1 point at the origin. Now what is this? Given that there is a point at the origin, what is the probability that point phi, without considering that point, has 1 point at the origin? Okay, so this means if you consider that point, there will be 2 points. So given that condition that there is a point at the origin, what is the probability that there are total 2 points at the origin? okay, or one extra point at search. And so this we have to also compute, and that we don't know what its value will be because we haven't studied the conditional probabilities. Okay. So if I define k dash as phi has 2 points at the origin, then you can say phi palm reduced probability of k is equal to the palm probability of k prime. Okay. A conditional point, I have to look at their 2 points at the origin. Now we will come back to the marked Poisson point process. So what is a marked Poisson point process? You can guess a Poisson point process where the points are marked uh, is known as the marked Poisson point process. And an independently marked Poisson point process is a point process underlying point process as a PPP. You can also have dependent marking also. Independent marking of a point, but let's focus on the independent marking. Independent marking of a point x with mark m uh, can be seen as an independent displacement of x to a new point x comma m in the space R cross. Okay, so if you see that you have a point and you assign a mark, so you are expanding the coordinate x comma m, and that's a point in the R cross m dimension. So it just means that you are taking this point and putting equivalent point in this space. So this is like a displacement. So we have proved that independent displacement of x result in a PPP itself. So the mark point process is nothing but a independent displacement of points. So it is also a Poisson point process. Okay, with a modified intensity measure, the Campbell message measure. So independently marked Poisson point process is also a Poisson point process with modified intensity measure or Campbell message measure. Okay. To show this, we have compute the Laplace function of the marked Poisson point process. So the Laplace function of marked point process can be similarly computed. Remember that for a normal point process, Laplace function is given as expected value of exponential minus summation of fxi. Here, in the marked point process, the coordinates are actually xi comma mi. So this will be defined as summation of fi f xi comma mi. So this can be any function from RD cross mark space. And I'm assuming the underlying PP has a intensity measure capital lambda. So for that, what I first do is I convert this exponential summation to product of exponential form. So this can be written as product of overall points, so exponential minus fxi mi. Now, what we can do is we can break this. Yeah, and we notice that the points are actually coming from the original point process. So instead of writing this product over all xi mi belongs to phi tilde, I can just write it xi belongs to phi. Right, where phi is the corresponding point process, the underlying point process, which I know is a PPP. This will help us to solve it further because I know this function is Laplace function. So this function is PPP is Laplace function. So what I do now here is I take EE672A product over all points. Now note that this phi tilde it has two randomness. One is phi and then another is the mi's given xi. So I break this expression in two parts. One is expectation is equal to phi, and then expectation with respect to mi goes inside the product. Because this does not depend on mi if I know all the points or if I know all phi. So now this is expectation with respect to mi given xi of this term condition on xi. So let's note that this function, when I compute the expectation with respect to mi, this will just be a function of gxi. So if I write instead of this as gxi, this will be expectation of e phi of product over gxi, which is a PGFL form. So it will be just exponential minus 1 minus gx lambda dx. This is noting that phi is a Poisson point process with this density, with this intensity measure. Okay. Now remaining is to compute this gx. So gx, if you look at, is the expectation of this function. So this is just integration of exponential minus fxm of new x dm. Okay, this is the probability distribution of m. Can you integrate it over the homework space? So if I write that back also, what I get is Laplace function is given as exponential minus 1 minus integration of exponential minus fx nu dx lambda dx. Okay, so there are multiple ways you can write this. One is this one. Second is I can just use the fact that integration over m of nu dx is just 1. So I replace that and then I can take this term common. So I get 1 minus exponential minus fxm and then nu xm and lambda dx. And we note that if the Campbell matrix measure is this dxtm is equal to this. So instead of that, I can write this. This is just lambda functional exponential minus integration of 1 minus exponential minus fxm into lambda Campbell matrix measure, which just tells the number of points, that points are in dx and the marks are in dx. Okay, so this is in the this is a Poisson process PG Laplace functional with the intensity measure. This okay, this just proves that the mark point process is nothing but a PPP with this modified PPP with this intensity measure. It is also interesting to note a second form, that if I instead of writing this, if I just write it exponential, I'm given x of this one. And that is also used many times. That just to note that this term is nothing but the expectation of exponential minus fxm with respect to the mark distribution given x. This is the palm distribution of mark. We are going to cover a very important theorem, which is known as Livniak theorem, and it is for PPP Poisson-Pond process. It deals with the palm probability of a marked Poisson-Pond process with universal margin. What it says that if we condition on a point of a Poisson-Pond process. So conditioning means we are conditioning on the fact that there is a point at a particular location and see the neighborhood, but without considering the point itself. So we condition on there is a point at a particular location. We'll go to that point. We look around the neighborhood, and by looking at the neighborhood, we do not consider that point as a part of the process. Okay, I mean neighborhood consisting of the rest of the points. Then this neighborhood would exactly like as seen from the same point uh, in case of the unconditional Poisson-Pond process. Okay, so if you go to the same location and there is a Poisson-Pond process without any conditioning, and if you look at that, whatever the distribution of that process is, that would be the same as this conditional distribution. Okay, so this means that if you consider a point process and you consider a universal marking, then the palm probability of reduced palm probability of that process is same as the normal probability. Okay, so PPP condition on a point without considering the point is same as PPP without any condition. So formally, it is written as let phi denote a Poisson-Pond process and let P be a property of point configuration. Okay, it means P is a element of the sigma algebra on N. Okay, so this is belongs to this is a set of all possible configurations. Okay, so P is just a subset of configuration. So P is a property of point configuration. You can either state in terms of a particular property that the point process has 2 points in this ball, or point process has a neighbor within 10 meters, something like that. Or you can explicitly write a set of some point configuration and you define that as a P. So it says that the probability condition on there is a point at x of phi minus that point. Okay, so I remove phi point at x from phi, So probability that this new point process has the property P is same as probability that phi will have that property. Okay, and this removal of point is defined because you have condition on this. So there will be always a point x. So phi will always contain x. So the phi set minus x will just mean you remove that point from the phi. Okay, so and recall that this is a palm probability. It means that the probability that phi minus root x has property p, right? Phi set minus x has property p, condition that phi has a point at x. So this is Leibniz theorem, okay? And this helps us at many places wherever you have to condition on location of a point. You can just remove that point, and you look at the property of the rest of the point, and that will still a Poisson property, okay, with the same density. So you can actually could do calculation using the same whatever we have learned until now. Okay, so how do we prove this? I will not go to the complete proof, but I'll give a sketch. So consider a PPP. Let us take a point x0. Okay, make a small ball around a point x, obtaining only x. Okay, only this point. Now the point, sorry, around x naught, I'm obtaining only x naught. Point inside the ball and outside the ball are independent. Okay, why? First of all, you have to prove that this is a stopping set, and then you have to prove that the area and then there's the area this and that are this joint, so they are independent to each other. Okay, so if I remove this point, remove any point in this set, right, in this ball, that has no effect on the neighborhood around the ball, right? Because the point process in this ball and outside the ball are independent. So whatever I do inside the ball does not affect anything outside. So I can remove any point in this ball. So I can remove x naught basically, and it will not affect the distribution outside. Okay, or I can have a point here and it still does not affect the outside. Okay, so conditioning on this point has no effect on the probability of the property as long as the property does not involve anything from anything which is going inside this ball, okay, or anything on these points. Now if I take this ball radius going to 0, okay, then it means this ball inside of the ball will only consist of this point x naught, and the rest will be outside. So you can extend the argument saying that whatever is occurring at x0, whether there is a point or not, that is not going to affect the point process. Okay, but this is generally not true for any point process, right? If for a general point process, conditioning on the fact that there is a point at x will change the distribution of points around the point, right? For example, binomial point process. If you condition on there is a point, it will change the distribution of the rest of the point because there are now only n-1 points. But for PPP, we have this property that it does not make any difference owing to the point independence and the area independence. Okay, so let us see some examples. Consider a homogeneous Poisson point process with density lambda 10 per meter square. So if I take a square of area 5 meters square, how many points are there on the average? There are the mean number of points in this area is lambda into size of A. So it will be 10 into 5, which is 50. Okay, now suppose origin is there, this these are axes and origin inside. Now condition that there is a point at the origin, how many points are there in A on the average? So if there is a point at the center, uh, how many points are there in A on the average? So we know that conditioning on when we are conditioning there is a point at the origin, that is not going to affect the rest of the point. The rest of the points are still going to be Poisson with density 10 per meter square. So total number of points, average number of points would be 50. Okay, and then there is a 1 point already there. So 50 will be the rest of the point. I said that you have to remove that point which you are conditioning on. So if you do not consider this point, then the rest of the points are Poisson, and they will be 50 on the average. So total number of points in this square will be 51. Okay, so you can say that conditioning on there is a point at A, it is 51, and can reduce intensity measure. If I remove that point, then they will be, rest the point will be 50. Okay, if the consider point Poisson point was not stationary, then also you can apply. So other than that, the number of points will be lambda A, and then so you have one more point, so it will be 1 plus lambda A. Now let us talk about another example, which is nearest neighbor distribution of a homogeneous Poisson point process. So consider a homogeneous Poisson point process with density lambda. Consider a point located at x. The nearest neighbor of the point is defined as the point closest to x. Okay, so nx is defined as you calculate the xj minus x for every point xj in phi. Okay, and you of course do not consider x, because if you include that, that will be 0. So I just take all the rest point in phi, compute the distance, compute the point which will give me the minimum, and that will be my neighbor. And the nearest distance will be just the minimum of this, the distance of nx from x. So I want to compute its distribution. Okay, so the CDF of the nearest neighbor distribution would be given as probability that dnx is greater than d. Okay, so sorry, CCDF. And then to compute this, you have to condition on phi has a point at x. Okay, because then only the neighbor is defined. Once you consider that there is a point at x, then only you can compute the nearest neighbor from it. Okay, so this you can also write that there is a palm probability of x uh, of minimum that this distance is greater than d. This is the nearest neighbor distance. Okay, and when I say this, note that this is the implicit conditioning that x is a point in phi. So how do we solve this further? Right, if it's a stationary process first, we will notice that if I shift the point process, then it's not going to change any difference in the distribution. Okay, so we can shift the Poisson point process to the point itself, making the point at x as the new origin. Okay, so if this is my observation point, I will just shift my origin to this, so this point will become at the origin. Okay, and the distance of the nearest neighbor is invariant to the shift, because distance with relative distance of the point will not change. Okay, so and again the point is stationary, that is why I'm doing it. So I can just compute the nearest neighbor distance of the point at the origin. Okay, so what I want to say here is the nearest neighbor of point at x is has the same distribution as nearest neighbor of the point at the origin. So I will just compute this, and this will be probability that the minimum distance of points from origin is greater than d, conditional there is a point at the origin. Okay, so if it's a stationary, instead of looking at the point at x, I can just look at the point at the origin. Right, it's not going to change any distribution. Okay, so now I'll write this formally. Uh, Right, now if this xj minus o, then this is just xj, norm of xj. So I'll just write the norm of xj is greater than d, condition that phi has origin as a point. Okay, and if you look at this, this will be xj belongs to phi, and xj is not equal to x, and x is origin here, so xj is not equal to origin. Okay, so this means I am looking at every point, but I'm not looking at the point I am conditioning on, and the rest points I am choosing the one with the closest distance. Okay, so this, if you look at there, I am talking about a property of the point process which is conditioned on a point, but when I'm looking at the property, I am not considering the point I am conditioning on. Okay, so this will have the same distribution if I look at the unconditional point process. Okay, which is same as probability that minimum of xj belongs to phi, xj is more than d.
So I remove the conditioning, I remove this point, and I get this, and it will have the same distribution as this. Okay, this is from the Sibonacc theorem. Now, what is this probability? It just says the minimum point, sorry, the the minimum norm of xj is more than d. Okay, so what is the probability that the closest point from the origin is more than d distance away? And here there is no condition. Okay, so this is same as saying that there is no point in the ball of radius d. Okay, if there is no point in the ball of radius d, then the all xj will be outside d, and if there is a point inside d, then this condition will not be true. So it is same as saying that the minimum distance to any point in phi from the origin is greater than d, which means there is no point of phi inside this ball of radius d with center at the origin. And we know this probability. There is no point in this as a probability, void probability, which is e to power minus lambda into size of this ball, which is pi d square. So this is exponential minus lambda pi d square. Okay, so and what I'm going to use here is location of the point does not affect distribution of d, and the occurrence of the point also does not affect the distribution of d and x. Okay, so this will be the distribution of the nearest neighbor of a typical yeah, and then if there is a location or any other point also, if it's a stationary point process, then the distribution of the nearest neighbor uh, distance of a typical point located anywhere is also the same. Okay, and note that this is same as the contact distance distribution. Okay, which contact distance distribution is the distribution of the distance of the closest point from any arbitrary location. Okay, so that is same as the distribution of the nearest neighbor's distance from any typical point for Poisson point process. Okay, so for PPP both are same, and that is because of the Sibonacc theorem. So it just means if you go to an arbitrary location and find the closest point and measure distance, that on the statistics it will be same as if you go to a particular point and look at the nearest neighbor. Okay, because occurrence of that point is not going to affect the rest point distribution.